Okay, so this is the next virtual lecture for EAPS536. The topic is the transformed Eulerian mean, which will hopefully have some meaning to you. It probably doesn't right now. Hopefully you've read a little bit through Vallis. The reading is Vallis E, chapters 9.3 to 9.4, as well as leading into chapter 12.1, which will apply this to the real atmosphere. All right, learning outcomes for today is to describe how the transformed Eulerian mean differs from a regular Eulerian mean. Explain the relationship among wave activity, EP fluxes, EP flux divergence, convergence, and acceleration, deceleration of the zonal mean flow, and describe how these concepts are relevant to our real atmosphere. So the next lecture we'll get into finally thinking about how we can understand the really overall general circulation of our atmosphere with these concepts. So this is a second largely theoretical lecture, but it's really important. So I'm hoping it'll also be shorter than normal. Okay, so key terminology for this lecture is transformed Eulerian mean. It helps to first talk about just Eulerian mean. So remember the concepts of Eulerian versus Lagrangian derivatives. Lagrangian meaning moving with the flow, Eulerian meaning at a fixed location. So when we talk about taking an average, any normal human being, usually you're thinking of an Eulerian mean, which is the normal way you take an average. And helps you to think about eddies or deviations. So this is an average at a fixed location in time, such as the annual mean, and or in space, which for example is zonal mean. So you might write this, say, for a meridional flow as V, the total flow. You can decompose that into some sort of a mean, an Eulerian mean, and a deviation as an eddy. And so when we talk about a transformed Eulerian mean, which is we often use a shorthand TEM, it's really a modified framework that lets you directly link eddy effects to changes in the mean zonal flow. So it's a really clever tool that we'll go through. And so formally, as you'll see, is that we're moving the eddy PV flux effect out of the thermodynamic equation, the buoyancy equation, and entirely into the momentum equation. So formally, that's what we'll be doing. So I just want to review, last time we talked about the eddy meridional PV flux, which can be written as the EP flux divergence. So this is all from last time. I'm not going to review this, but V prime Q prime bar we can write as equal to del dot F, the divergence of this EP flux. And this EP flux, Elias and Palm flux, or if you want to think about it as the wave activity flux, has this form where in the meridional direction, the J hat direction, is the meridional flux of zonal momentum, and then the vertical component of this flux, the K hat direction, is a meridional flux of buoyancy modified by F naught over N squared. And so just remember, so this governed the direction of wave motion. This also followed the group velocity of the Rossby waves, which is pretty remarkable, this flux vector. So it just tells you where wave activity is moving, essentially. But so for right now, what we want to talk about is this idea that there are two components to the EP flux. The meridional eddy PV fluxes are related to both the meridional fluxes in the zonal wind or zonal momentum and meridional fluxes in buoyancy. And which of these do eddies actually do? So what does this mean? Or is it both? So we're going to go back to the individual equations for each. And I'm actually going to say that at the end of this lecture, I don't think we're going to even really fully answer this yet. But we're going to talk about an important framework for thinking about this and trying to simplify things a little bit. Because this is, if you feel like this is pretty complicated and hard to understand, it is. And so there's a lot to think about here. So let's go back to the individual equations. So at the end of the day, we can show that remember that the eddy PV flux is actually an eddy momentum flux and an eddy buoyancy flux. So let's go back and think about those two things separately. So the Eulerian mean, zonal mean equations, which is to say the regular equations that you usually think about for a Boussinesque fluid. We can write here the zonal wind equation, du bar dt, with the advection terms, the Coriolis terms, and then these eddy flux terms on the right-hand side, and a source or sink term. So you might think of, we usually write as F because it's most often a friction. And then the buoyancy equation, which is a dB bar dt. So again, think of this as thermodynamics, as heating and cooling. Warmer things are more buoyant. generally in our atmosphere. And so the advection terms, again, eddy flux terms, and then we have a source term. So the zonal wind, again, at the end, at this F bar is friction, and then this S bar is a heating. So you can think about variations in heating generating variations in buoyancy. So just as a quick note, the V bar here, so we're thinking about zonal mean. So this is purely ageostrophic flow. And so this is really referencing here the meridional overturning, essentially. So you can have, say, poleward flow up high and equatorward flow down below. So for example, the Hadley cell, yeah, poleward near the tropopause, equatorward near the surface. So let's think about the quasi-geostrophic case for this to simplify things. So we're going to neglect vertical eddy flux convergences, so terms with the W primes. So in our QG equations, again, the horizontal flow is much, much stronger than the vertical flows. And we're going to neglect ageostrophic velocities, so V bar or W bar, except when you're multiplied by F naught or N squared. And so just to note, the N squared is dB bar dZ. So that W bar, dB bar dZ we keep, and then F V bar we keep, because these are both important in the quasi-geostrophic framework. Okay, so the result then is this simplified set of equations we're going to write here. You'll notice we dropped the advection terms as well. And so we want to remember that thermal wind balance relates U bar and B bar together. So F naught times the vertical shear of the mean zonal wind is related to minus the meridional gradient in buoyancy. So remember, as always, it's good to remember where this comes from. It combines the geostrophic balance of the meridional flow. So I should say, in the meridional direction, it's the zonal flow balanced with the Coriolis force acting on the zonal flow, balancing the meridional pressure gradient, and then hydrostatic balance in the vertical. And so the key thing is here, so you can see now in these equations, we have the individual eddy fluxes of zonal momentum and the zonal equation of buoyancy in the buoyancy equation. So because of thermal wind balance, though, you have to remember that so the eddy momentum fluxes can change U bar, and the eddy buoyancy fluxes can change B bar, but both of these then can relate to each other via thermal wind balance. So when you change U bar, you're changing B bar, and when you change B bar, you're changing U bar via thermal wind balance. So because you're assuming the flow is a balanced state. So for example, if you increase the wind shear of the zonal wind, then you're going to increase the meridional buoyancy or temperature gradient, as a simple example. So that's really annoying. We still don't really know how the eddy fluxes change anything at all, because there's eddy fluxes in both, and then they both affect the mean, and those affect each other. So can we get to something that's a little bit... All right, so let's look at our equations here. And so what we want to emphasize, what we're going to do is point out that in the buoyancy equation, so we have this minus n squared W bar term, which is really adiabatic cooling or subsidence warming. Or you can think of it also as the advection of theta contours as air goes up or down. And then the S bar term is a diabatic heating term. So you can think of that as solar insulation, anything that's heating the fluid. And so in the extratropics, what's important is that for both of these equations, what's shown in the blue boxes are the dominant balances. So in the zonal wind, you have the Coriolis term, or Coriolis torque on the meridional flow has to be balanced by eddy fluxes of momentum. So that tells you that to have an overturning circulation, you need to have eddy fluxes of momentum to balance that in the zonal mean. And so, because of course in the zonal mean, there's no more zonal pressure gradients. If you're thinking about where did the pressure gradient term go, say for geostrophic balance, that's why. And then in the buoyancy term, it's a balance between this adiabatic cooling term and again the eddy fluxes. Meridional eddy buoyancy fluxes. And so meanwhile, this F bar and this S bar with these source sink terms, which we haven't really talked about much, are typically small residuals. So you don't have to usually think about them. But when we talk about S bar, it's small, but it's really important. It's actually what drives the mean meridional overturning circulation. So what do we mean by that? So for example, in the tropics, we learned about the Hadley cell. So the Hadley cell arises because you have differential heating. So you have variations in heat, diabatic heating, and so you have variations in buoyancy, and that's actually what's driving the meridional overturning circulation in the first place. And so the question is, can we transform these equations to a more useful form that accounts for this residual term S bar? So it's a small residual, but it's actually fundamental to everything in terms of thinking about why we have overturning circulations in the first place. So let's try to absorb this. Okay, so what do you end up with? So we did this derivation. So the top two equations are our original Eulerian mean equations for the zonal mean zonal wind, 9.45a, and for zonal mean buoyancy, the dB bar dt equation. And then on the bottom now is our transformed Eulerian mean equations. So you'll notice, so we'll walk through. So what's actually different here between these two equations? You'll notice there's zonal wind and buoyancy, and then below that are the equations for our residual flow. So that residual circulation, V bar star and W bar star as well. So just as a reminder of where those come from, but we're really going to work with just the du bar dt equation in particular, as you'll see in a moment. So what's different? So if we look up in the Eulerian mean equation, we had our original F naught V bar minus our ddy V prime V prime bar. And so really what we're doing here is, if you recall the eddy PV flux, that's V prime Q prime bar is given by these two terms. Again, we've mentioned that the eddy PV flux is really it represents effects of variations in the eddy momentum flux and the eddy buoyancy flux. And so what we can do is we can rewrite this term. So we're replacing V bar with with V bar star. So you'll notice now there's this extra term here. So I'll connect this as dashed right arrow shows you. So we're plugging in our equation for V bar star to remove V bar. So we have V bar star minus now this extra term. And then for the minus ddy of u prime v prime bar, our eddy momentum flux term, now we're using our eddy PV flux equation to replace that. And so something magic happens when you do that, which is that the eddy buoyancy flux terms now cancel out and disappear, and you're left with this F naught V bar star. So the Coriolis now acting on just the residual circulation minus just the PV fluxes themselves. And so that's where we end up here. So you'll notice the difference between these two equations here. So we've replaced a ddy u prime v prime bar with just a v prime q prime bar, which might sound like a lot, but it's simpler. And so it's simpler for a second reason, which is that you'll notice that this in the buoyancy equation now, the eddy buoyancy flux divergence term is now gone. It's disappeared. So it's not in the second equation. So just have it highlighted, or in the transformed Eulerian mean equations. So I have it just highlighted in the regular Eulerian mean equation. So we've effectively moved the eddy buoyancy flux divergence term, V prime, B prime bar, or the one that has that term in it, into the momentum equation, kind of magically, and combined it with the zonal momentum flux divergence term with the U prime, V prime bar. So and so the end result, again, is so what pops up as new in the transformed Eulerian mean, the TEM equations, is we have a single eddy forcing term, which is the eddy PV flux V prime Q prime bar, that directly changes the zonal wind. So we now have a really clear, direct relationship between what eddies are doing, and in fact, to both momentum or buoyancy, and how that is related. That's through via PV, its eddy PV fluxes directly to du bar dt, to the acceleration or deceleration of the zonal mean zonal flow. So that's pretty remarkable. And we had found a similar-ish form to that last lecture, but here we have a really, really nice clean du bar dt equals on the left side, and the right side v prime q prime bar. Okay, so now that we have this equation thinking in terms of just PV fluxes, we can now link back, or eddy PV fluxes, we can now link back to the concept of wave activity and the EP flux from the last lecture. So this is really kind of the last big linkage here. So we can bring up our equation for the zonal mean zonal wind du bar dt for in our transformed Eulerian mean framework. So we have that v prime q prime bar on the right-hand side. And let's simplify things and just think about no external forcing. So there's nothing, really no friction in general in this case. So we're going to focus on our eddy PV flux. So we can write this using our definition of the divergence of the Eliason-Palm flux, which is being del dot f is being equal to v prime q prime bar, just to emphasize that f is a different f, don't forget, than what we just canceled out in the first equation. So that's our EP flux here. And so we can write our equation in this way, and then I just following Vallis, he moves the Coriolis term for the residual meridional flow to the left-hand side. So we can do now is one more step, which is to bring back our wave activity equation, dp dt. Remember, p is our wave activity plus del dot f, which is really just the advection term, essentially the movement of the wave activity at the group velocity. And then the right-hand side is sources or sinks of wave activity. So if we combine these two equations together, CO 9.73 and 9.29, you can get rid of, you're basically solving for del dot f in 9.29 and then plugging that into 9.73 and rearranging. You can combine the u bar and the p terms. So you get a ddt of u bar plus p minus f naught v bar star is equal to the source sink term on the right-hand side, d. So why is this interesting, and how is this going to be useful? So recall that the wave activity P, I had introduced it as a term called pseudo-momentum. And now you're seeing exactly why. So this is why it's called pseudo-momentum, is that this wave activity, P, acts dynamically like a zonal mean zonal momentum per unit mass, so a velocity. And if you go back to the equation for it, it has units of meters per second. So when we say momentum, don't forget, we're saying momentum per unit mass, which is a velocity. That's why it's UVW. So P is also, this wave activity somehow has units of a velocity, and so you can think about it in that way. That's why we call it pseudo momentum, because it's like a momentum essentially, but it's not a true zonal momentum, but it shows up that way in the equation. Okay, so the key step is that we can use these equations now to understand a lot about how the mean flow is affected by the eddies. And so we've said that a few times, so now it's time to actually put these equations into practice and think about some really simple conceptual examples of going through what the math says from these equations and how we can interpret it. So let's think of a really simple case. So let's put up our equations for the wave activity on the top, and then our new combined u bar plus p equation on the bottom. So case one, and so we're going to think about a case of no sources or sinks of wave activity. So d will be equal to 0, and steady motionless waves. So del dot f is equal to 0. So what I'm showing on the left here now is just like, let's think about, you can think of this, if you will, as a mean zonal flow for the northern hemisphere, for example. But let's suppose you have some flow field that looks like this. So you have like a jet-like feature at middle latitudes, and then you have some easterly flow, so negative zonal flow at lower latitudes. But this doesn't have to be specific to this case. So what we're doing is we're saying d is equal to 0 on the right-hand side, so there's no sources or sinks of wave activity. And steady motionless waves. So you might have waves in this domain, wherever they are, they're not moving. So I didn't plot them on here. You can imagine your own set of where waves are occurring and just pretend that they are not moving at all. So what does that mean? And so there's one additional step, is for this case, there will actually be no residual circulation either. So V bar star is equal to 0. So and so what does that leave us with is, so the top equation gives us that dp dt is equal to 0, which means the wave activity doesn't change. Wherever you have waves or wave activity, it just stays constant at every location in space and time. Or I should say constant in time at whatever it is. It's fixed in space. From the second equation, since dp dt is equal to 0, then du bar dt is equal to 0. So everything is 0 in equation 9.74, except du bar dt. So this means the mean flow doesn't change either. So your u bar would not change at all. So this is called the non-acceleration result, which is to say that the mean flow is not accelerated at all, regardless of where wave activity is found. So you can, just because there are waves doesn't mean they do anything. And that's a really key point here, is that so waves alone, the existence of waves doesn't actually change the mean flow at all. We have to think about waves being able to move around. And we know that the waves are going to move around, but so in this hypothetical case, we can show that if the waves didn't move around, if you just had a fixed wave field, it wouldn't do anything to the mean flow at all. It would not be accelerated. So what if the wave could move around? So case 2 is so north sources or sinks of wave activity, and we're going to think about simplify things for a barotropic fluid, which is to say that you have no mean meridional motion at all because everything is constant with altitude. And so I've superposed on here now a profile of wave activity that might be similar to what we see on Earth, for example, but we'll come back to that. Is wave activity, and that should actually be positive definite, should really not go below 0 at all, just to be clear. So we're saying no sources or sinks of wave activity, but we are allowing the waves to move around. And since it's barotropic, we cannot have a zonal mean meridional flow at all, whether it's residual or not. So we don't have any zonal mean meridional flow, so that term goes away. So now let's think about what these equations tell us. So first, from the first equation, is that the dp dt is equal to the convergence of the wave activity flux, or the EP flux. So what we're saying here is wave activity. This is like an advection term, if you will. Wave activity simply moves around. They're fully conservative waves, no sources or sinks. So wave activity simply moves around, and it's going to increase where the EP flux converges and decrease where it diverges. So in this case, if you want to think on the left-hand side here, you have wave activity in the middle latitudes, and they're going to move. So we're going to move northward and southward, for example. So you're going to have divergence of wave activity in these middle region, and you're going to have so del dot F is positive, and you're going to have convergence to the north and south. As the waves move from the middle latitudes to north and south of it, to higher and lower latitudes. So del dot F will be less than 0 at higher and lower latitudes. So you'll expect then wave activity to decrease in the middle region and to increase to the north and to the south. And so our second equation says that so if wave activity goes up, the zonal mean zonal flow is going to go down, and vice versa. So you could actually separate these derivatives if you wanted to and say du bar dt is equal to minus dp dt if you wanted to. So this would actually, I haven't drawn this up here, but this is ultimately an exchange between zonal mean momentum and pseudo momentum. So if you have more pseudo momentum, you have to have less zonal mean momentum, and vice versa. So this would actually act to decelerate, to reduce U bar in the middle latitudes here, middle regions, and increase it, or excuse me, I should say, it would increase it in middle regions and decrease it at high, or to the north and south where P is increasing. So, but we're not even going to do that. I'm not going to put that on here because this is not realistic. This is just really a hypothetical case to think about movement of waves in general, because something has to generate and potentially dissipate this wave activity in the first place. So why otherwise the wave activity would just move away to infinity? Where does it go? In the real world, we have things that generate and dissipate waves. So why does this matter? Is that this means that sources and sinks of wave activity are fundamental to changing the barotropic mean flow. So something has to, for waves to move around, which can change the zonal mean flow, we need something to create waves in the first place and destroy waves also. So let's go to something that's a little more realistic, which is steady state wave activity in a barotropic fluid. So again, we're simplifying things. We're not having this V bar star, or really V bar in general. We have no meridional flow. And so what's nice to think about the steady wave case is this idea that P, your profile of P here, is constant in time. So there's some source of P in the middle region, and then there's a sink of P to the north and to the south. So what's the result here? So let's think about our top equation, think mathematically through this. This says that the divergence of the EP flux, or the wave activity flux, equals your magnitude of your source. So wave activity diverges away from where it's generated, so your source, where D is positive, and it converges towards where it is dissipated. There's a sink of D. So we go back, we have our same wave activity fluxes as before, but now you are imagining that wave activity is moving away from this middle region, and it exactly balances the source of wave activity. So where your source region where D is positive. Okay, and so let's link this now to du bar dt. So we can say from our second equation that du bar dt is equal to the divergence of the wave activity flux, which we had actually shown in the previous lecture, which is equal to D. So this is really the huge connection here, is the zonal flow then will be accelerated where waves are generated. So if you have a source of waves, if D is positive, then du bar dt will be positive. And it'll be decelerated where waves are dissipated, where D is negative. Du bar dt will be negative. So, and a key takeaway also is that this means irreversibility, so which is to say not just waves moving around, but waves being generated or waves being destroyed in particular, is an irreversible process, and it's essential to how waves affect the mean flow. So here this is really the critical result to think about here, is that where you generate waves, because the waves move away, actually, you are going to, waves are moving from a source region to a sink region, and that is going to, the generation of waves accelerates the mean flow, and the dissipation of waves weakens the mean flow. And so this is the really big connection between linking all of these concepts together of the eddies, and this EP flux and their divergence and convergence and the mean flow itself. So how does this manifest itself in our actual atmosphere? So we're going to have a little bit of a taste of this here, and then we're going to cover this in the next lecture. So this is a really nice figure it's figure 12.2 from, so this is now starting into chapter 12 of Vallis Essentials. So it's shown here as a northern hemisphere view, where in the middle latitudes, you have zonal flow, and so it's shown on the right-hand side is the profile of zonal flow, and really the middle latitude part's really important there. Is this zonal flow is eastward in the middle latitude, so you have relatively high zonal momentum there. And so we talked about there's a source of wave activity, so which is to say waves whose amplitude is growing. So what do we need for waves to grow in amplitude is by baroclinic instability. It implies an unstable growth of waves, from infinitesimally small waves to larger waves and larger waves that also eventually break into nonlinear eddies. So this is where baroclinic instability of the jet stream at mid latitudes becomes really fundamental here. And so we use this term stirring, because you can actually think of this process. Imagine standing outside of the Earth. The Earth is in your palm of your hand, and you're just literally stirring up and creating waves in the middle latitudes. This, you can think of it as an external process that stirs the fluid, creating waves. So that process alone, then, it acts to converge actually zonal momentum towards their source region. So this momentum is taken from lower or higher latitudes where the waves break and dissipate. So this is how this all comes together, is that this stirring, baroclinic instability creates waves. The waves, creates waves or stirring that generate waves in the middle latitudes. Those waves move away from the stirring region towards higher or lower latitudes, and that the net effect of that is to converge momentum into the stirring region itself. So in essence then, baroclinic instability of the mid-latitude jet, we talked about it before as a negative, or I shouldn't say a negative, as a way of breaking down the jet into eddies, but remarkably, it also helps to sustain the jet's existence. It's actually in the process, these waves are converging zonal momentum back into the jet itself. So these are happening simultaneously. It's simultaneously trying to break down the zonal mean jet into eddies and also restore its zonal mean state. This is pretty remarkable. And we're starting to really connect everything together here in terms of thinking about how the eddies arise from the mean state, and then, or the waves themselves, and then how the waves actually act to help sustain the jet from which they emerged in the first place. All right, so some other questions that we're going to cover in the next lecture. So can we now try to apply these concepts to understand really the large-scale circulation of our atmosphere in general? So we talked about the jet stream. Let's think about this. We'll talk about this in a much more applied sense for the atmosphere. Where in the atmosphere do real eddies actually transport momentum versus heat? So buoyancy. So again, yeah. So we'll come back to that. How does the global momentum budget fit into this? So one thing we haven't talked about yet is, so we just said how eddies can act to generate the jet itself. Why doesn't the jet, that would imply that the jet would just increase in intensity forever. So there's obviously something that has to constrain, has to provide a sink of momentum for the jet. And then where does the ferrule cell come from? So this is this indirect circulation, overturning circulation in the extratropics. Where does that come from, and how can we understand that? In particular, in the context also of this transformed Eulerian mean formulation. So we'll cover this next lecture. Just a couple quick notes to finish on is there's a really nice summary of the TEM equations in the box in Vallis E, page 186, so right at the end of chapter 9. You can go to. And then one note is that I didn't cover here, but is hopefully something that maybe you're wondering about or you're just completely confused about, is this meridional buoyancy flux, which is part of the PV flux. We're basically saying it acts like a force. So it's part of, if you have a meridional buoyancy flux that actually acts to accelerate or decelerate the zonal flow. So why in the world that should seem very bizarre and magical. If it doesn't, you should think about it a little more and be confused by it. So I just highlight that there's a short section in Vallis E, section 9.4.3, that addresses this topic. And ultimately, the buoyancy flux acts like what's called a form drag that arises when you have sloping interfaces that places a stress on the fluid. So it's a sink of momentum. It's a pressure-based drag that arises. It can occur with, for example, mountains as well. And so the transporting heat or buoyancy basically acts to change the slope of these pressure surfaces. And so it's going to act to change this form drag. So you can look at that a little bit more in the book as well. Okay, so go ahead to Blackboard and answer a few questions about this topic.